Yeah, so let's start this morning's session. So Carlos Simpson is our first speaker from Côte d'Azur, University of Côte d'Azur, and the title is Parabolic Higgs bundles corresponding to the Hecke eigensheaves appearing in the geometric Langlands program. However, I believe there's a little special case because Carlos promised us last night.
No.
You start with
Thank you, guys. We look forward to seeing the presented results. So thank you very much. Thank you very much to the organizers for the invitation. It's a great honor to speak at this celebration of conjectural mathematics. So I'll be talking about the part which I know about a lot, which is his paper on self-duality equations, and also his paper in Duke Math Journal introducing the Hitchin system. So let me just say, so for myself, it was an actual paper on self-duality equations was a gigantic revelation for me. And then when I visited Oxford, I also my understanding augmented exponentially even more. So yes. Okay, so what I'd like to talk about today. So I'd like to talk about today is joint work with Donagi and Tony Pantev about the geometric Langlands correspondence. So the geometric Langlands correspondence was started out for GL2 by Drinfeld, and then Lemont sort of expanded and refined Drinfeld's paper. And then this was done for GLN by Franco Geitz-Goyegel. I mean, Arinkin was maybe the first case I think of doing this for non-compact curves. And it's related somehow, although I'm really completely not an expert on this at all, somehow related to the Langlands. I mean, I understand how, roughly speaking, but related to the Langlands program in arithmetic geometry that's worked with Drinfeld before. Both Lafours, Go and others. But in what we'll be talking about is working in a complex setting, so we're not talking about L-addic sheets. Okay, so now I'd like to just go back to what the correspondence says in basic terms. And actually, we found a post on Math Overflow by Will Sullivan, which asks exactly this question. So we'd like to just reduce this to a sort of a concrete question rather than something about derived categories and stuff like that. So just in very concrete terms, the correspondence is supposed to be saying that some cases are proven and other cases not, but this correspondence is supposed to be saying that if we start with a local system which we'll call lambda with a given structure group over the Riemann surface, C, we start with a Riemann surface, then that's supposed to lead to a perverse sheaf or a D-module on the moduli stack Bun of principal bundles for the group, but not the same group, but the Langlands dual group. Okay. So this is the basic construction. So we have an input local system lambda on the curve, and we get out a local system we get out a perverse sheaf on the moduli stack. Okay. Now what condition is this perverse sheaf supposed to satisfy? Well, it's supposed to be an eigensheaf for the family of Hecke operators, which depend on the choice of point in C. And since the family of Hecke operators depends on the choice of point in C, which, roughly speaking, in a certain way, they commute for different points. They commute. So we can think of sort of simultaneously diagonalizing these operators. And so the eigenvalue is going to be a function of C, but in this world, it means a local system on C. So it makes sense to say that the eigenvalue for this eigensheaf should be this local system lambda. Now, why is this some kind of topological information? Well, geometric and topological information. Well, this perverse sheaf, although that's a kind of a complicated structure, nonetheless, a perverse sheaf is going to have an open set where it's a local system. Okay, and then the question of Donagi and Pantev is to say, okay, what happens if we apply the nonabelian Hodge correspondence to this local system on the open set? Then we'll get a parabolic logarithmic Higgs sheaf. So that's kind of the question. Okay, so the Donagi-Pantev program says, okay, there should be a nice description of the resulting things. So these parabolic logarithmic Higgs bundles. And one of the interests, although of course the case we're going to talk about today is not at all in such generality, but the idea would be that if you have a canonical way of describing what this is, then that should, in principle, generalize to any group. Okay. So this is the potential. I mean, eventually, although we don't have that at all anyway so far, but then, well, maybe in a certain way, I guess their theorem to provide points is kind of a new case. But the case we're working on for genus 2 over a compact curve is not. That was Drew's original paper. Anyway, but part of the idea is that potentially this might generalize to general. I think we'll see in the course of the talk what are some of the problems where there's technical complications to do that. So Ron and Tony carried this out in their paper, which is an asterisk volume at this point, called Parabolic Higgs eigensheaves. They carried it out for the case of rank 2 local systems on P1 minus 5 points, in which case the moduli stack button is itself a moduli stack of parabolic objects. So in our work, they kind of graciously invited me to participate. So in our work, we've been looking at well, you might say next case. It's a next case in terms of dimension of the moduli space. In the case of P1 minus 5 points, the moduli space, the moduli stack button has dimension 2. In the case of compact curve C of genus 2 and rank 2 local systems, the moduli stack of bundles has dimension 3. So we've been looking at that. Okay, so in this talk, C will be a smooth projective curve over the field of complex numbers, and at some point we'll say the genus is 2, but some of the stuff that we'll say here works for any genus. Okay, so and then we have let's take a reductive group G, and then we have a moduli stack bun G of G bundles over the curve, and the semi-stable bundles, that's actually an open substack of the substack, although it's compact in a certain way. But anyway, it admits a universal categorical quotient, which is the moduli space. And this MG, that's a compact space, moduli space of G bundles. So part of the idea here is that even though this moduli stack button G is kind of a somewhat wild object, it's not that bad, but it's not a finite type, it's only locally finite type, because of the fact that bundles can have arbitrary amount of instability. But we're kind of ignoring those parts of the moduli stack and just looking at the open subset where it's semi-stable and we can get a nice moduli space. Now in turn, this is going to have the open subset of stable bundles, which is a fine moduli space. The moduli space of semi-stable bundles is not a fine moduli space that contracts different semi-stable things that have the same Jordan-Holder quotients. But if you look at the moduli factor of stable bundles, then it's a fine moduli space. So which doesn't really mean it has a universal boundary, but almost. Because the stack can be a non-trivial juror, and what we say, I said we don't worry about that. Actually, that does cause us a little bit of worry. In the case of rank 2 bundles with even determinant, the moduli space is P3. But there's no way of writing down a family of bundles over P3. It's known that even on any open subset that's obstructed by the juror. And so it kind of causes a problem. You can't actually write down the bundles that you're talking about. Okay, so that's kind of a bit of a difficulty, but nonetheless. Okay, now the geometric Langlands program is going to therefore construct D modules on the stack when G, and we can restrict those to the stable bundles. And as it turns out, there's a subset of the stable bundles called the very stable bundle, on which it's known that the D module is supposed to be smooth anyway, the local system. So it's already known. I mean, known in the theorem cases and conjectured in the conjecture cases, it's known what is the open subset where it's supposed to be a local system. And this definition was basically introduced by Lemel, but I just during the talk I noticed that in Lemel's paper at some point he said this was in a letter from Grunfeld to Lee or something like that. So maybe we'll shape that out a little bit more precisely, but maybe Langlands attributed this to Grunfeld, the letter from Grunfeld to Lee. So the definition of a bundle is very stable if it doesn't have any nilpotent Higgs field. In other words, nilpotent endomorphism with coefficients in the bundle. So it turns out that those are stable. Okay, that's a theorem that very stable implies stable, which is not completely obvious. Now that's the open subset, and Donagi and Pantev said, okay, let's look at the divisor, which is the complement of this thing. And they introduced the kind of fun terminology, which is if it's not very stable, then it must be wobbly. Okay, so that's now called the wobbly locus, the wobbly divisor. Okay, so that's the wobbly divisor is therefore the locus of bundles that do admit a nilpotent, a non-trivial nilpotent Higgs field. We'll see more about it. Okay, so now we can kind of describe more precisely the topological content of the geometric Langlands program just viewed in this very simple way, which is that we get a construction of local systems over this open set of very stable points, and more precisely, the input is this local system lambda, which is the eigenvalue. The output should be a local system over the open subset. And the program is to try to apply the Donagi and Hodge correspondence to look at these. Okay, so now we're going to let's call this X. So C is the curve, and X is the modular space of the bundle. Okay, so let's call that X. It's kind of unitary character, right? Okay, and for us, G is going to be a linear type of a group like either SLN or PGLN, and it's going to be 2 fairly soon. The construction is designed to work in general. Some parts of the construction, as you'll see, are just kind of general considerations, which would work. That's kind of the point. Okay, but in our case, it means that X is going to be a moduli space of vector bundles on the curve with some conditions on the determinant. Then let's call W the wobbly locus. So we'll be looking for a construction of local systems on the complement. Now let's just go back a little bit and have a slide about the Hitchin equations and everything. So mindful of his famous paper, introduced gauge field equations for a connection with an additional term, which he called the Higgs field. And one of the motivations was that was a reduction of the 40 usual Yang-Mills equation. This led us, to a gigantic amount of work by a whole bunch of people. So one thing, I think this was really, in my memory, this was something that I really thought of either during the time I was at Oxford or just like right after we got back or something like that. The idea that or at least like fully seeing this as like nonabelian Hodge theory, somehow it came to me, but just after visiting Oxford. So, I'm not sure, I don't think you guys said, oh, Carl, this is nonabelian Hodge theory. But we were discussing with just the discussion that it just kind of led to that basically. Okay, so but I think what we're doing here is it actually illustrates pretty well the philosophy of using the Hitchin equations to transform topological questions into algebraic geometry questions. Okay, so a solution of Hitchin's equations, we can just write them down. It's a gauge, it has a connection, that's del plus del bar, and it has the Higgs field P, which has its adjoint P bar, P star, and H is the metric. So, you can either think of this as having a fixed metrized bundle, C infinity bundle, and looking at for connections, that's the gauge approach. Or you can think of it as having a fixed holomorphic bundle, E comma del bar, and looking for metrics on the holomorphic bundle. Well, anyway, once you have all this stuff, so once you have a solution of the equations, then in some depending on your viewpoint, but in some viewpoint might just say the equations just sort of say that D is a flat connection. Once you have a solution, then you get a flat connection, and you also get the Higgs bundle, which is a holomorphic bundle plus the Higgs field. Good. So in one direction, if you start with a polystable Higgs bundle, this is what was done in Hitchin's paper. you can get a solution. And if you start with a local system, then in Donaldson's paper that came right afterwards, you can also get a solution. And this was done in Kevin Corlett's thesis in general. And then there's a Bachman formula to show the fluid harmonicity of the harmonic map, and that's how you get a harmonic bundle of higher dimension. So for these reasons, we'll call, because it's related to harmonic solutions of harmonic mapping equations, we'll call this whole collection of data a harmonic bundle. Now, over compact Taylor manifolds, then you can get a one-to-one correspondence between semi-simple local systems and polystable Higgs bundles. And there's this condition which really comes from Donaldson's Yang-Mills theory in the unitary case. Condition that the C1 and C2 should vanish. Of course, all the Chern constants, once it's flat, all the Chern constants vanish. But the thing you need to check is, the main thing you need to check is the C2. Of course, we obviously want the C1 to vanish. Maybe I should just say, and there's a Vogelmalm easier inequality that says that if the C1 is 0, then the C2 is positive. And what you're looking for is C2 equals 0. So you're looking for the lowest piece of that. You're looking for the lowest value that's allowed by the Vogelmalm zero inequality. So that's not an easy thing to do. It's not an easy thing to find the smallest possible value. That's not you have an inequality. Anyway, so now this is, I think, completely fully generalized by now by Takuro and Mochizuki to the case of non-compact, quasi-projective varieties. So if we have a smooth projective variety and normal cross-link divisor, then you can make a correspondence between the semi-simple local systems on the complement and Higgs bundles. So what kind of Higgs bundles? It means they have to have a parabolic structure. They have to have the Higgs field has to be logarithmic with respect to the parabolic structure. And if you want to make this correspondence work out in this way with local systems, then you need to make a condition called totally imaginary on the Higgs field, on the residues of the Higgs field. And of course, there's still this condition about the vanishing of the parabolic Chern constant, which is really the main thing that needs to be checked. Okay, so what is a parabolic structure? It means that we have a bundle over the compact variety. Means we have a bundle over the compact variety. Then you have filtrations over the components of the divisor. If the dimension is 3 or more, you would have a condition about the filtration is having a common splitting. And the Higgs field is supposed to be logarithmic on the bundle and respect the filtration. The parabolic waves are, I guess, well, Ron and Tony have convinced me that I should change this. I'm sorry. Those should probably be called levels rather than weights. Anyway, some real numbers associated to the parabolic, the steps in the parabolic filtration. Those real numbers are in terms of monotomy, those real numbers are the argument of the angle of the monitor. And the totally imaginary condition says that the Higgs field has residues. Since it's logarithmic, it has residues. It says that the residues should have totally imaginary eigenvalues. But actually, in the case of what we were talking about, those the eigenvalues will actually be 0. So it means that it doesn't mean that the Higgs field is 0 on the gradient of the parabolic filtration, but it means that it's nilpotent on the gradient of the parabolic filtration. And it's the type of this, the nilpotent part of the residue of phi, that determines the nilpotent part of the monitor of the associated connection. Okay, so Donagi and Pantev have proposed then to conjugate by this Kobayashi Hitchin equivalence to conjugate the predicted geometric Langlands correspondence. So remember that the correspondence has an input and an output. So the input is the local system, which is supposed to be the eigenvalue. That's now viewed as a Higgs bundle on the curve. And the output, well, the output is supposed to be a reverse sheaf on the moduli space of the bundle. It's what the output is going to therefore be one of these parabolic logarithmic Higgs bundles on X with respect to the wobbly divisor. Now, the input thing is going to correspond to a Higgs bundle, and we're going to assume that that lambda is a general local system, so it corresponds to a general point of the Hitchin base, the base of the Hitchin vibration. By that corresponds to a line bundle over the spectral curve. And since the point is general in the Hitchin base, The spectral curve is smooth, so we'll call that scintilla. Then on the output side, we're looking to construct, let's say, a D module on bun G, which, as we said before, has singularities along the wobbly divides. And just a comment, which is that, in fact, in Lamont's paper, he actually explains that the characteristic variety of the D module is actually equal to nilpotent. And that was the case for GL2. So, conjecture for GLM, and it's expected to be the case for any structure group.
How do you know that the singularities along that wobbly place are logarithmic?
Well, so so I guess kind of an equivalent question. I mean, that's equivalent to asking, how do we know that the D module has regular singularity? I think that's just part of the statement. I think that if we started with a local system on the curve that had irregular singularity, you can do that, people do that, then you would expect, I guess, to get irregular singularities. But thank you, I didn't say that, but the condition of the Higgs field is logarithmic. That corresponds to having the D module with regular singularity. And you can also have D modules with non-regular singularity and Higgs fields which have high over poles and stuff like that. That's the kind of wild observation. But originally this came from, well, I guess, yeah, not quite. I guess I'm just kind of assuming that. I'm assuming, I mean, just kind of from here, my knowledge comes from just sort of hearing people talking about stuff. I've never heard anybody say, oh, a local system on the compact curve is going to lead to a wildly ramified Asperger sheet on that. So
I guess you will give a construction of it. Maybe it's given construction.
Well, so as it turns out, we can see in our, you can see in our construction the way the logarithmic thing comes out actually. So that's maybe not the answer, but just in terms of geometric Langlands theory, program theory, so the completed objects that we're looking for are Higgs bundles on X that have a parabolic structure over the divisor W and Higgs field having, you've asked, logarithmic poles along the divisor. So now one of the difficulties here is that W doesn't have normal crossings. So we're going to need a method to resolve singularities. And Mochizuki's theory actually helps with that because it gives us Lefschetz theorem. So you have Lefschetz restriction theorem, you can chop down to a surface. Then on the surface, it just means you have to only resolve the singularities which are codimension 2 in X or codimension 1 in W. So we'll just keep this notation of X and W, bearing in mind that at some point, well, there's going to have to be some resolution. So we'll be discussing that a little bit. Now, in the higher dimensional situation, there's still a Bobin-Laurent-Roman correspondence, namely, logarithmic Higgs bundles are going to correspond to sheaves on the logarithmic cotangent bundle, whose support, which we'll call the spectral variety, is finite and dominant over X. So if we're looking to construct one of these things, it's logical to start by looking to construct the spectral. So that's supposed to be a finite covering of X that has a birational inclusion into the cotangent bundle. It has poles, corresponding to logarithmic poles, with some kind of inclusion, birationally at least, into the cotangent of X. Yeah. And so this is an amazingly obvious thing to do once you say it. Okay. And Thomas Hausel actually has Thomas Hausel said that he sent me some mail late 1990 saying, oh, we should do this or something like that. But anyway. But so their proposal was, okay, we're looking for this thing which is supposed to be a subvariety of the cotangent bundle. And we actually have the cotangent bundle. It's the Hitchin moduli space, Hitchin Itsuri, we should remember that Itsuri gave the first algebraic geometry construction of this. The Hitchin Itsuri moduli space of Higgs bundle. So we can call it M Dolbeau, this kind of Dolbeau part of non-Hodge theory. In terms of, if we have a general group G, then it's the moduli space of pairs consisting of a principal G bundle plus a section of the adjunct bundle with coefficients in G. This has a Hitchin vibration, which is a proper map from the moduli space to an affine space. The nilpotent cone is the inverse image of the origin. and we have a C-star action and so on. As we saw yesterday, really, the C-star action collapses the moduli space to the nilpotent cone, and so it sends most of the points to X, which is the zero section. Okay. Well, so our point in the base of, if we have a point in the base of the Hitchin vibration, it corresponds to a spectral curve. The fiber of the Hitchin vibration over that point is a set of Higgs bundle, such that the spectrum of the Higgs field lies in the spectral curve over each point of C. And this is such a Higgs bundle is determined by BNR data, Boolean sigma Raman data of a line bundle on the spectral curve. Now, on the other hand, so that's for a general point of the base. If we take the origin of the base, you get the nilpotent cone, and that's also known to be a Lagrangian subset for the symbolic structure. It has several different components. So each different component is the downward flow of the outgoing directions along the component of the fixed point set, which is to say the downward going directions of the C-star action. You get an ordering, and the lowest part of the ordering is actually the moduli space X itself, which is the zero section of the cotangent. And now the wobbly locus, I think this is not maybe completely accurate. About that, but almost always the wobbly locus is just the divisor, which is given by places where the other components of the nilpotent cone meet this bottom component. So in the case of the 5-point case that was done before, the wobbly divisor actually had normal crossings in codimension 2. But in general, as we see in this project, we can have other singularities, and the ones we've seen so far are cusps and tangent. So we can also say that the very stable points are places where the upward flow is a closed subset. And the wobbly points on the converse are the places where the upward flow meets another component of the fixed point set. This fixed point set is a star. Okay, so now this is just a slide to recall that I think you guys know is that this was the Duke. The moduli space of the Higgs model is the compactification of it's really a relative compactification of the Hitchin map on the cotangent bundle of the moduli space. But by rationally speaking, we can kind of identify these two things. Okay, so now we're looking for subvarieties of the moduli space. We're looking for subvarieties of the cotangent bundle, but birationally speaking. But so we're looking for subvarieties of the moduli space that are finite coverings of X. And well, we have them sitting right in front of us, which is the fibers of the Hitchin vibration. Okay. So general fiber of the Hitchin vibration meets the inverse image of the general point of X in finitely many points. So that's exactly what we're looking for. Okay, now let's see. Okay, so now I wanted to just put a slide here to say what is the property of the thing that we're looking for? Okay, so the property is that it's supposed to be a Hecke eigensheaf. So the Hecke correspondence, this is kind of, as we'll see in a minute, not exactly right. There's a little bit of a twist. We'll see in a minute. But basically, the Hecke correspondence is the correspondence from X to itself that depends on a point of the curve C. So we can write it as a correspondence between X and X cross C. So the points of the Hecke correspondence is both space H. Those parameterize modifications. So remember, X is a moduli space of bundles. So if you take a bundle and you do an elementary transformation at a point, sometimes called the Hecke transformation, then that changes it to a different bundle. And the point is in the part of, which is called C there. And the fiber of H over a point X cross C, it's a set of all possible choices of that subspace on which you do the elementary modification. So in the case of rank 2 bundles, the fibers of those, the fibers of H are P. So now the pullback push forward operation for that diagram gives us an action on constructible sheaves or on D module. And the Hecke eigensheaf is something which roughly being again, has the property that when you apply this pull back and push forward operation, you get back the same sheaf, exterior tensor product with the eigenvalue sheaf on the curve. We call it pulling back, push forward. We pull back from X, we push forward to X cross C. So if we have V on X, then the push forward is going to be something on X cross C, and it could very well be box times the same thing on X, box times with the eigenvalue on curve C. If it has that property, then it's called eigen. And so, you know, if this is your first contact as it was for me a while ago, it seems kind of surprising. Why would you have a solution to this thing at all? Well, it turns out you do. We're constructing them and so on. You know, they're constructed by Rintel, of course. It seems a little surprising, even if we say, okay, these are commuting operators and so on. It seems a little surprising that there would exist such a thing in the first place. But that's, I guess, the fun part of this whole picture. Okay, so the geometric Langlands conjecture predicts that if we're given our input local system on C, which in terms of derived categories is used as a scribe paper sheaf on the moduli space of local systems, then there should exist a unique eigensheaf. So, you know, I know there's all these things about coherent sheaves and stuff like that, and the relationship between derived categories is not exactly correct as was originally formulated, and so on and so on. What we're doing here is just extremely rough. So we're just taking a generic choice of lambda. We're saying, let's just try to look at the local system that you got on the very stable open subset. So we don't need to worry about all this incoherent sheaves and X squared rows and blue and so on. At some point in the future, you would have to worry on that, but for now. So roughly speaking, we need a construction which starts with the local system lambda and produces a D modulo open above. Okay, so now remember that there's the thing in the dual group. I think I switched the groups around here. So the lambda thing should actually be an LG local system. And I'm just writing out here some of the, I'm not sure these are all the possible references, but this correspondence is known in many cases, many more cases than what we're doing. However, it's not known completely for general groups. Okay, so and we don't really have a geometric description of the basic operation of what happens. So that's what we're looking for. And so their program is trying to construct as we said so far, trying to construct the parabolic logarithmic Hitchin that you get. So Tomasz said to me, oh yeah, I suggested this to Donagi in letters or something. I heard a talk by Paul Haynes in the Lean conference in 2005, where he was saying very vaguely something that kind of really vaguely suggested that you might have big bundles on the moduli space of bundles, whose spectral variety was were the fibers of Hitchin vibration. Whitten says stuff like this sometimes. If you're interested in that studies and like you're walking and Whitten goes that direction, he says, oh, you know that you can construct big bundle by using the Hitchin, you know, the fiber of the Hitchin vibration. Oh, okay. Anyway. So yeah, so this has kind of been known a little bit. But now in particular, there's something called electric magnetic duality in a paper of Kapustin and Whitten, which gives us really more precisely the relationship between the input local system lambda and the BNR data for the Higgs bundle. So let's look at this a little bit. So there's a theorem, which we'll see on the next slide, which tells us that if we look at the Hitchin vibrations for the group and for the dual group on the same curve, then they share the same. There's the base of Hitchin vibration is naturally isomorphic, and so this is known for any reductive group. So that's already an indication there's something. I mean, that this is a strong indication that the Langlands duality statement is going to have something to do with the Hitchin vibration. So we can write this like that. I call these dueling S, Y, Z vibrations, right? So this thing which is called electric magnetic duality, not only do they share the same Hitchin base, but in fact they're generically, you know, on the places where they are tori, they're S, Y, Z dual tori. So in other words, the torus, the abelian variety fibers for the group G and for the group LG, they're dual abelian varieties. They're naturally dual abelian varieties. Okay. Now, what does this mean for us? I'm going to say this on the next time, but let's just look at the picture for a minute. What it means for us is that we started with an input local system lambda, which is a Higgs bundle. And it's Higgs bundle, let's say if we set things up in this way, it's Higgs bundle for the group LG. Okay. You see here, even though the group really is going to be SL2 or PSL2 or something like that, it's good to distinguish between LG and LG to try to understand what's going on here. So our input thing, which is what I'm calling E, that's the Higgs bundle associated to the local system lambda. Our input is a point on the fiber, on the Hitchin fiber over some point in the Hitchin base. Okay, it's a point in the Dolbeault moduli space of LG. Okay, now if you use this theorem, that tells you that that point over on the G side, you have the same point at the base. You look at the abelian variety, which is the fiber over that point in the base, and the fact that these are dual abelian varieties tells us that that point corresponds to a line level on the other abelian variety. And so if you remember, that's exactly if we're going if the leftmost abelian variety is supposed to be our spectral variety, that's exactly the thing we're looking for. We're looking for a line level vector. Okay, so this electromagnetic duality really tells us that this is going on. Okay, now I'm just sorry, it's a little bit repetitive, but I'm just recalling that the correspondence predicts that if we have a LG local system lambda, there's supposed to be a D module. If lambda corresponds to a point, I'm just repeating what I said previously. If lambda corresponds to a point at the Dolbeault moduli space for LG, then it's going to correspond to a line bundle on Y0, which is the Hitchin fiber in M Dolbeault of G. I should have put a G. Okay, and so Donagi and Pantev said, okay, let's just take this line bundle, which is the dual of the point, and say that that's going to correspond to a logarithmic parabolic Higgs sheaf on X. Okay, so now recall that the G Dolbeault moduli space is the cotangent bundle, birationally speaking, of X. And so we can write a diagram like this, which is, so this is only birational, okay? But roughly speaking, the Hitchin fiber Y0 is a subspace of the logarithmic cotangent bundle of X. So we just view that as the spectral product. Sorry, it's just repeating what I just said. We need to, the BNR data that we're looking for is a subvariety, which is this Y0. We need a line bundle, and the line bundle is going to be the dual line bundle L. So that there's some modification that's going to be needed because of the blow-ups. So let me just draw this picture. So now this is the picture of how we're going to get the spectral. Okay. So this is the Hitchin moduli space, but it's also T star of X actually. There's some places where the map maps to the wall, where there's points in the, so Y0 is the fiber over our point D, our general point of Hitchin base. That's going to be our spectral variety. There's going to be some ramification of that thing over the Wally divisor. And in fact, what really happens is that you actually have to blow up Y0 in order to get a well-defined map. Then once you blown up, you have an exceptional divisor, which becomes the ramification divisor. So here I wanted to put, I just took a screenshot of a page of Lamont's paper. This is Lamont's paper in the same volume of Duke Math Journal as Hitchin's first paper about the Hitchin systems. Okay, and so Ron, when we finally realized this, Ron said, "Oh yeah, but I remember when I looked at that, I said these are the same numbers." But I don't know if anybody else looked at this. I didn't, but the same numbers appear in both papers. So in Lamont's paper, at some point he says, "Okay, Delete actually calculated the Euler-Poincare characteristic and obtained such and such an answer, and therefore M of B is the multiplicity of the bottom piece of X in the characteristic divisor of the B model." What that means is it's the generic rank of that local system that we're looking for. I'm telling you, this is page 351 of the Duke Math Journal volume, the same volume in which Nigel's paper, the first paper about people. So there you have it, 2 to the 3d minus 3 is the generic rank of the local system that we're looking for. And in the same ball, I don't know, Nigel, did you put 2 to the 3g minus 3 in that paper? I don't remember.
Not in that context, but
No, as the degree.
I probably did.
The degree of this map, right? If you take the Hitchin system, you take a point of the Hitchin base, you look at the fiber graph, it's in going right. You map that down to X, which is the lowest component of the moduli space. You map it by 1. That's because it's C star X, right? But it's equivalent to saying you take the C star action. That's a finite map. What's the degree of that finite map? Well, it's 2 to the 2d minus 3. Which is not for the case of genus 2 or 2 goes degree 8. So those maps have, this map has, here we have a subvariety of the cotangent line, whose degree over the base is equal to the rank of the local system that we're. I mean, how could it possibly not be the spectral variety of the thing? So I mean, I can just stop now, but anyway. Okay, so
What kind of push down are you supposed to do in order to get down? Is it the naive push forward, or is it more complicated?
no, it's not push forward because that's just a finite. This is a finite cover. We're taking line. We have line on Y0. I mean, from electric magnetic duality, right? From the other picture, from our point E, we have a line on Y0. So we have a line limit, and we just take the push forward line. That tells you the Higgs bundle over a general point of X. So there is a subtlety involved here, of course. There's a subtlety involved, which is that you have to take the push forward, but then you have to put an appropriate parabolic structure on the resulting thing. You get something which is kind of a meromorphic Higgs bundle. You get something which is a Higgs bundle over an open subset, and it has natural bundle over an open subset, it has a natural Higgs field and so on. But you don't know how. You need to know how to complete it to something which will satisfy the Suzuki theorem. I guess the Suzuki theorem came after the paper, so you couldn't really do this at the time. But so it's definitely how to decide what parabolic structures to put on around the boundary, which is to say the law, which is what that's what we're doing.
Do these blobs that you were alluding to, they amount to somehow replacing the cotangent model with a log cotangent model?
Yes, exactly. Well, more or less exactly. This is, I'm talking about something a little bit repetitive here, but this just says what I just said. We have a subvariety, we have a line limit, and we take this var pi thing, that's that projection. We take the var pi lower star, and so I'm papering over here at an issue which I'll get to in just a little while, which is that you have to blow up to get this map var pi to actually even be well defined. But once you blow up, then you can do that. The only thing is that once you blow up, you get an exceptional logic, so I have to modify the line limit by some multiple of these exceptional logics. That's what needs to be calculated. Okay, so the main idea of Ron and Tony's program is to say, okay, let's take this Hitchin pi to Y0 and use that as a spectral line for its Higgs sheaf on X with the spectral line limit determined by electric magnetic duality. And so this is what we just said. We need to do a little work on the parabolic structure. But so we can formulate a conjecture, which is that this would be a general conjecture, which is that whatever happens, the Higgs sheaf that we define above, which is well defined in a meromorphic sense, that should at least be in a meromorphic sense the Higgs sheaf corresponding to the local system, which you get by the geometric Langlands correspondence. And more precisely, if you can define in a natural way the logarithmic and parabolic structure, then that should be the thing that corresponds to the local system. And so Ron and Tony proved this for P1 minus 5 points. And we've proven that the paper is not completely out yet, but almost proven it for the case of genus 2 group. So let's see what that happens. Now let's just discuss a little bit the case of genus 2. Maybe we'll see a little bit why this helps us. Okay, so let's recall the moduli space of rank. When I say genus 2, it's rank 2 bundles on a curve of genus 2. These moduli spaces were explicitly described by Zariski 101. That's kind of the introduction to the theory of moduli spaces of bundles. So Zariski 101 showed that the degree 0 or degree even degree moduli space of rank 2 bundles with trivial determinant is P3. Okay? The locus of strictly polystable bundles, namely ones that aren't stable, is the Kummer quadratic surface, which depends on the curve C. Now, here's where this twisting thing comes in. If you want to look at the degree 1 moduli space, so the moduli space of line bundles of determinant that has degree 1, then well, that determinant is going to be a line bundle. Let's say, suppose it's OC of P. I mean, it could be OC of P plus Q minus R or something like that. But let's suppose it's OC of the point P. That's what fits naturally with Hecke correspondences. That a priori is going to depend on the point P. Of course, they're all isomorphic, but when you make the isomorphism, you have to tensor with something which is a square root. And so that's why this moduli space, which I'm calling this calligraphic X of 1, which maps to the curve C, the fiber over a point is the moduli space with determinant OC of P. And that becomes trivial when we pull back to a 16-sheeted finite Étale cover. That's why when I was saying at the start, thinking about the Hecke transformations, that's not 100% exact in this situation, but okay. And so we can also explicitly describe the wobbly divisors. So the wobbly divisor was extremely well known, and this appears in Griffiths and Harris, the last part of Griffiths and Harris. It was known, I don't know, probably a century ago or something more. The wobbly divisor in the X0 is the union of the Kummer surface with the 16 things called the trope plane. So there are 16 P2s that touch the Kummer surface along to order 2. So the Kummer surface is a degree 4 surface. But so a plane is going to a priori is going to intersect that in a degree 4 curve. But there are some planes which intersect that in twice a conic. Those are called trope planes. There are 16 of them. They form the classical Kummer 16-6 configuration. The Kummer surface has 16 nodes. Okay, there are 16 nodes and 16 trope planes, and each trope plane has 6 nodes, and each node has 6 trope planes. And my comment here is how many were going to St. Ives, right? Anyway, okay, so that's the Kummer 16-6 configuration. Now inside X1, the wobbly locus is actually an irreducible divisor, but it has nodes and cusps. So it's a divisor which is basically the same 16-sheeted covering across P1, but it's an image of that divisor, and it has nodes and cusps. Okay. So now we can see here, now we see the singularities. So the singularities inside X0 are tachyonic, basically. Of course, there's more singularities at the 16 nodes of the Kummer surface, but those are in codimension 3. We can ignore them. In codimension 2, the singularities of W0 are the tachyons where the Kummer surface meets the trope plane. The trope planes themselves intersect in normal crossings, so that's okay. In WP of 1, there's some nodes, but that's okay. But we also have, I'm sorry, this should say cusps. We have some nodes. Nodes are fine, but the problem with the cusps. Sorry, that was. Okay, so now here's where I think you guys were asking about this. So it turns, as you probably know, the downward flow map from this Hitchin fiber down to X is not well defined at certain points. Those are the points which really lie over the wobbly locus, which is to say there's any point that flows down to a fixed point set that's different from X. In other words, a higher level fixed point set. Those points are not going to have a well-defined map to X, so you have to blow up those points. And in our situation at rank 2 and genus 2, that can be done explicitly with a single blow up. So really there's 16 points that need to be blown up in the X0 case, and in the X1 case, there's a curve called, it's the fiber product of C bar with C tilde, which we call C hat. There's a smooth curve inside the prim variety, which needs to be blown up. And now when we blow up, we get an exceptional divisor. I'm sorry, it's the same notation E, which is not great, but here this is the exceptional divisor of that blow up. That becomes a part of the ramification of the map. Now, because of this ramification, it turns out that the Higgs field on the very pi lower star of the line bundle becomes logarithmic. Maybe I'm not explaining that here, but that's true. Essentially, because there's a spectral one form on the abelian variety, which when you blow up still is a one form. So that has to be logarithmic. Now, what about parabolic structure? So on x1, we introduce a parabolic structure with weight alpha equals a half. And on x0, we don't actually put any parabolic weight, as it turns out. This is something which there's a third construction where you do put a parabolic weight, but that's not the right one for getting a Hecke eigensheaf in this particular setting. So on x0, we don't put any parabolic weight. That means that the Higgs field has logarithmic poles, but it has logarithmic poles that are upper triangular, and you get a unipotent monomer and you have the local system. But parabolic structures do show up when we resolve the singularities of the tachyons. So kind of inside the tachyons, there are actually parabolic. Then the work we have to do is to basically adjust the choice of line bundle so as to get the parabolic turn classes to vanish. Then we apply Mochizuki's theorem and get a local system. So, yeah, maybe I'll skip over this part. That was some theory. Well, let's just go to here. That was some theory to say what I'm about to say, but we'll just okay, so let's go back and look at the Hecke correspondence. So really, this is the good version of the Hecke correspondence, which goes from the straight x of 0, which is a three-dimensional moduli space, to this curly x of 1, which is a four-dimensional thing, which fibers over the curve and is isotrivial, but it's not actually trivial. But it's basically basically a single x of 1 across the curve, except there's this twisting by a 16 group of order 16 and so on. That's because of the fact that there's no uniform way of trivializing the tensor, choosing the line bundle to tensor with to trivialize the determinant of the bundle once you've done the Hecke transformation, which is uniform in the curve in the point P. You have to choose a root. And this is the Hecke transformation. It's a set of elementary modifications of bundle. And the maps. So you can do this in both directions. You can go from x0 to x1, or you can go from x1 to x0. We're picturing here the x0 to x1. So, and remember, we're trying to solve this equation, the r h lower star of g upper star of the v0 thing should be the v1 thing, box times with the pullback of lambda. And again, this box times needs to be understood in terms of pulling back to that 16 sheet of cover. So now we'd like to verify this fact. So maybe just I'll probably be finishing here pretty soon. This sort of explains why I needed that theory. Okay, so if you go back here, right, we need to calculate this RH lower star. Right, so we need to pull back. Maybe I'll go back once again. We need to pull back by G. So G has relative dimension 2. We need to pull back by G. We construct our parabolic logarithmic eigensheaf on x0. We need to pull back by G. And then we need to take the R1 pi lower star along H. So H in this case is a map that has fibers that are P1. I guess the H is the fibers H, there actually are. There are lines inside the tree. They're actually in fact they're lines of the quadratic line complex. So basically that means that we need to be able to calculate the cohomology of our constructed perverse sheaf on those P1s, which are the lines inside P3. And we'd like to have a Dolbeau way of calculating. So we need the Dolbeau calculation of the Hodge activity. So the answer, this was what was on those theory slides, is that we define the relative Dolbeau complex, H over X, which is just so here this E, the E that shows up here, that was maybe I was called a script E before. That's the E that we got by pulling back from the X 0. You define global complex, but this is an algebraic geometry thing. It doesn't even have any differential to it. The differential in the complex is just multiplication by the Higgs field. The fact that this has length 1 is due to the fact that the relative dimension is 1. So in general, you are going to be higher, full complex and so on. And then the Dolbeault theorem. So that's something that we proved in the paper in 2016 with Ron and Tony, including parabolic structures. Right? You need to do this, talking about parabolic structures also. And so, so this is the direction. I'm not going to have time to say this, but basically, the idea of being able to do this calculation is that basically, if the relative Higgs field on each fiber has isolated zeros, then you have a subscheme of zeros of relative Higgs field. That becomes the spectral covering for the Higgs bundle for the higher direct image Higgs bundle. Basically, because this complex, maybe I'll say, maybe I have this next slide. Yeah. Basically, because the Dolbeault complex is actually a Koszul resolution of a sheaf, which is supported on those points where the relative Higgs field is at 0. And so the higher direct image becomes just a usual direct image. Anyway, just an R lower, just a H lower star of this G. Because E is cohomological degree 0, the E tensor 1H, that's cohomological degree 1. So this G thing is in cohomological degree 1. So the Dolbeault complex is quasi-isomorphic to just G, but put in degree 1. So if you take R1 pi lower star of that, that's just H lower star of G. Okay. The problem here, this is why we did this paper in 2016 with Ron and Tony, is that you need to talk about the parabolic structure that's introduced on that. I should stop. Let me stop here. But anyway, so we do that. The zeros that you can describe the zeros of relative Higgs field. They're the places where the Hecke modification, upstairs that in the Hecke body, they're the places where the Hecke modification is actually compatible with the spectral. That's what Donagi and Pantev called the abelianized Hecke boson. And so you can show that the abelianized Hecke correspondence actually decomposes as a product, as a fiber product of the spectral cover of the curve fiber product with the Y of 1 thing that we're discussing for constructing for the spectral variety of the constructed. Let me just finish with this slide. So we could also verify. So this was a question, but we were able to verify that this is the answer we get is the same as the answer of as Drinfeld original construction. Again, using this high direct image thing. Because Drinfeld's original construction was done by using Langlands transform. So we can kind of apply this technology of doing the higher direct image to this Langlands transform. So we can actually show that it's the same. I'm not sure, I'm not even sure what the references would be as to why. So there's a question in geometric Langlands correspondence. Is that thing unique? Is the eigensheaf unique? And it said that it's supposed to be, but I'm not sure if that was proven or if it's now proven or something like that. But anyway, we don't need to call on that uniqueness property. You can actually show directly that we get the same. So I'm finished.
So you consider the genus 2 case and trivial determinant. What about non-trivial?
No, that's there's both of them. Yeah. Good. So thank you for the question. Well, see the x0. That's the x0 is trivial determinant. The script x1. That's the band limitations with determinant as a O of p. But you can see you need to do both of them in order to be able to talk about the Hecke. Because the Hecke correspondence goes from one to the other and then back.
But here you need to the explicitness of the moduli space, which is the 3. Also here, explicit description of the space.
Yeah, so I mean, did I say, I think I put that on slide, maybe I didn't, forgot to say, the X1 moduli bases, those are intersections of two quadrants and two quadrants. Yeah, that's all. Yeah.
So related to that, I mean, how much of the geometry of the intersection of two quadrants are you using here? Because, I mean, this, as far as the projective bundle is concerned, there's an idea in 955 and this description in terms of triples of points, you know, and actually they're all given by, all the bundles, or generic bundles are given by Hecke transforms of those.
Oh, yeah.
So I wonder whether that's an input which would be useful.
Yeah, possibly.
He argued, I mean, this was before stability, this was his 1955 paper. But it's effectively saying that the quotient of the intersection of two quadrants by the action of the, you know, the 16, the H to H1 is a double covering of symmetric product of P3 branched over something, some 6 planes or something like that. But only recently I kind of figured out that looking at Donagi that actually what's happening is that all these things, the generic ones, are given by using those 3 points for Hecke correspondences.
Yeah.
I don't know whether it's useful in what we do instead of. But what I'm saying is that how much of the geometry of the intersection of two quadrants, which is very rich, of course, do you use?
Well, actually, we're using lots, so we ended up looking through the last chapter of Richard's and Paris to a certain extent. Yeah, so we're using to a pretty big extent the geometry of the quadratic line complex. Because the Hecke transformation is the quadratic line complex. If you take a point of x and 1, that corresponds to a family of, I mean, the point of x to 1 is a line inside x0, which is P3. So x1 really is kind of the quadratic line complex. So we need to use some stuff about that. I think, I'm not sure, maybe wrong, we can discuss this, but I think we did sort of see the fact that we have this kind of the x1 space has a quotient. We have the quotient by the group action.
Yeah.
I don't think we use the 3-point description. But I mean, so there are these group actions, and there's a question as to how much up or down you go with respect to the group action. So we've sort of chosen a middle ground here where it's not really SL, it's not really PGL2 local system, nor is it really GL2 local system. It's kind of halfway in between. It's sort of designed to be able to do the calculations as sort of as easily as possible to get to the real to the PGL2 final correspondence. You should go to the quotient.
Yeah, I have a question. So, do you have a proof of pure dimensionality of the multi-locus, or you know this for some cases?
Well, in our case, yeah. Yeah, I don't know. I think, as I said on the slide, I think there's a very few number of cases where the description of the model locus is not exactly the same as what I said. I don't remember what those are looking like, or I do.
Or maybe the shaky locus. I mean, can you bring that?
Yeah. Well, so I mean, there is this fact that if you take the place where the component, you know, if you look at the nonabelian component, you look at it, so those the nonabelian component has a bunch of components, which they're all Lagrangian subvarieties, so they have the same dimension, and those intersect each other in codimension 1 pieces. And the reason for that is because the nonabelian component is a locally complete intersection, because it's the inverse image of 0 inside the Hitchin base, which is an Allen base. So if you have, you can't have things that you can't have divisors that intersect in higher codimension thing. You can't have set varieties that intersect in codimension 2 or 3 or something like that. That's not going to satisfy whatever the Ornstein property or whatever it needs to be a locally complete intersection. So once you know that the nonabelian component is a locally complete intersection, that implies that the spaces where the divisors join together have to be codimension 1. Now, what does that say exactly? Sorry? No, well, that's why we do, that's why we're doing this case. I mean, you definitely have cases where, I guess, cases where you have a component of the, nilpotent cone, which kind of meets another component of the nilpotent cone, because you might have a fixed point set of the seesaw action, and then a lower fixed point set of the seesaw action. When you slow down from here, it hits this one, then that continues to slow down. All sorts of bad things like that could happen. Those don't happen in this case, so we sort of ignore that. So we don't really know what type of bad behavior might.
So you said this, but, so you have to tune the parabolic weights to get the right trail classes? Are those weights kind of like universal, or they're gonna be the same?
Well, so as it turns out, they are going to be the same. So in the process of doing this, we actually kind of analyzed what was going to happen for any curve, even at higher units, but rank 2. Because in Drinfeld's paper, he discusses what happens in the value transform for rank 2 bundles over an arbitrary curve. And so from that, it looks like it looks like the parabolic weights have to either be 0 or in that case. In case of rank 2 bundle. Yeah, so I think in the case of rank 2 bundles, the parabolic weights are either going to be 0 or and it sort of depends on the pair. In the higher dimensional case, so we thought about this a little bit. So it looks like, but this is just a vague idea. It looks like the parabolic weights are probably going to be some kind of rational number whose denominator probably has something to do with the rank of the bundle because of the fact that I'm not sure, but I think it's going to depend on what happens when the C-star flow flows past the fixed point set. So if you think about the C-star flow flowing past the fixed point set, in general, the fixed point set corresponds to a variation of Hodge structure. In general, the cohomology, the tangent space is a cohomology. If that cohomology is going to have a sort of a Hodge structure of some string, which it's a weight 1 Hodge structure that has some string of Hodge numbers, so it goes negative. It's fine. In the case of higher rank, that could sort of be a string of arbitrary length. And the different weights of the C-star action in the neighborhood of the fixed point set come from that length, basically. I'm not sure, but it looks to me like those are probably going to affect the parabolic weights that you put on the thing. So probably those can be kind of, as the rank gets big, probably they can be sort of arbitrary rational numbers, I guess, but we're not,
Actually, in the last, I mean, you were referring to it in Houston's paper. So in the last, I think it's chapter 13 or something like that, they twist with the powers of the line bundle on bond G. I mean, is it possible to do that kind of thing here in your construction?
Maybe, I don't know.
Because I mean, that sounds like very interesting from the Chen Simon's point of view, get that line bundle.
Yeah, maybe. I guess I'm personally not a big expert in sort of geometric language folklore. So there's like a B field and that type of thing.
Yeah.
I don't know what it is. So that's possible, but I'm sure.
More questions? No? Okay,